Thank you. Thank you for the nice introduction, and thank you for inviting me and having me today. It is really an honor to be here and discuss my research for the past almost 6 years now in speech community. So I'm going to cover actually almost all topics which I worked in the past 6 years, some summary of that and the lessons which we learned over this like long journey. And main focus will be on efficiency. So you will see how this is connected to efficiency, but in all research, we are trying to think about how to make something simple, something efficient, and something usable in practice. Okay, so agenda for today, we will start from speech recognition. So who is not familiar, that means that you have a speech as an input and you wanted to produce some transcription. Then we will go to the generation where you have the inverted input-output. So now you have the text and you wanted to produce the speech for that text. And then I will go to the privacy, which is kind of like new topic for me for the past 2 years, but I think it's super important nowadays, having everything around us. And all in the core will be efficiency. So I will try to cover the things why efficiency is important and how we can make recognition, generation, and privacy efficient and how it's related between each other. Okay, so we start from efficient speech recognition, and that started exactly at my journey at Facebook when I was there a resident and then like did postdoc. And at that time, the main motivation for us was first is can we do large-scale experiments with speech? And at the time, we created the data sets, like which was titled as LibriLite, but eventually this is just LibriVox data, like recorded like books, where we like prepared the data set. It was around 60K hours, which was a lot of data at that time. Nowadays, it's not a lot anymore. Having the whisper paper, for example. But we wanted to understand how the unlabeled data can be used and how we can, get something out of that and what we can get out of that. So at that time, we decided to pursue this very simple technique, which is pseudo-labeling, self-training. So I will discuss what is it. Later, we switched to fully unsupervised training, self-supervised learning, and mixture actually of the like self-supervised training with self-training. Main motivation at that time is to understand the difference between architectures and loss functions, because we had like seq-to-seq models, transducers, CTC models, and at the time transformers just appeared. So we started to use transformers in speech. Okay, so what is self-training? So the simple self-training is the technique with like teacher-student like notion. So you have your labeled data, you train the model, and then you just pass your unlabeled data through that model. It gives you some labels. So we call it pseudo labels because it's not true labels. So now you interpret these pseudo labels as labels, and you just now continue training the model. So now you train a new model on the joint data of labeled and unlabeled data to produce better model. And you can repeat this process several times. And this actually very old technique. It was appeared in 1960, kind of. But the main question is how it's working for speech. People show that it's kind of helping, but not much. And the main question was, okay, now we at the better models at the bigger scale, is it working or not? So how we do this in speech? So speech is a bit more funny domain because you have both components, acoustic and linguistic. So you have your labeled data, you train your acoustic model, and now we often can integrate the language model into your acoustic model. So in that sense, we can say that you pass your unlabeled data through acoustic model, but then you can add additional language model to integrate it and improve your unlabeled data predictions. So here it shows that you can pass language model via the beam search decoder, for example, you can produce like transcription hello world. So now you have this labeled data, pseudo-labeled data. So you have your transcription. So now we just interpret this as a labeled data and we train a new model combining labeled and unlabeled data together. And we can repeat this several times and even maybe plug in another language model and maybe more powerful language model. Okay, so that was kind of first thing which we tried. And after we published the first work on first like large scale experiments with teacher-student training, Google also published the work where they showed this for the seq-to-seq models and additional thing in terms of like augmentation, how this augmentation influence the overall training. But for our results, what we first did is we tried to look at the scale. So we used the LibreSpeech 100K hours, and we use LibriVox as 60K approximately hours as unlabeled data. We investigated convolutional architectures and transformers, and also compared CTC and seq-to-seq models. As a language model, we decided to stick to the simple n-gram because it's efficient and fast, and you can like kind of scale to that amount of hours at that time. Okay, so first result which we saw is, first of all, pseudo-labeling and having the unlabeled data, it significantly reduced gap between the different architectures and between different losses. So here you can see supervised models on the left. You see that there is very big discrepancy between different architectures and also between like CTC and seq-to-seq. But then when we apply the unsupervised data, we see that the gap reduces and they kind of very close to each other, even if you compute the relative improvement between the models. What is interesting, at that time, we got the state-of-the-art result, which is now a bit joke maybe because number is reduced by a lot on LibreSpeech. So we got the state-of-the-art without any language model. So we got the same result as others, but without language model on top of that. And we got state-of-the-art result if you add additional language model. So it was a very nice result, but our state-of-the-art result was only for a couple of the months, I think. And then self-supervised learning came out and everything became more funny. But what things I guess important here is what we can learn with this unlabeled data. So the first thing is we looked into the scaling in terms of the amount of data. So you can see here that clean set on the LibreSpeech also improving, but it was not so hard data set. So we looked more on the noisy part. And here you can see that strictly more data improves performance, and it's not saturated yet. The second thing is you can ask how well your pseudo labels actually. So let's try to train now the model only on pseudo labeled data without the labeled data. And you can see that actually you perform better. So that means we are learning actually diversity from the unlabeled data, and it's already helping us to get better model and with the bigger data. If you combine further labeled and unlabeled data, yes, you get a little bit more improvement on top, which makes sense because your labeled data are graded and it's still helping a bit. Okay, now you could ask the question, what is actually we are learning with this unlabeled data? So for me particularly, it was interesting in terms of like, do we better model now acoustic because we have diverse set of the speakers, accents, and variation of the noise, or it's more about language model. Now we have just like more text data, so you just learn better language itself. So we come up with some like interesting observation is that if you shuffle the words in the sentence, you kind of destroy the linguistic structure. We can argue about how much of linguistic structure you actually destroy and if it's valid test, but it's kind of giving a notion if we like improving a lot of linguistic or at least n-gram structure. So yes, we have the unigram thing. Where is my, yeah, okay. So here. So if you try to look at a sentence and then like shuffle the words and you try to read it, which we ask actually some native speakers to read the sentence, it was very hard for them to record that because you have kind of employed language model in your head and you're trying to fill the gap continuation of the words. So it's really good test. So in our case, we decided to go with several like independent experiments. So we decided, okay, let's just use the segmentation. Here you have the issue that years of the segmentation and you cannot dissect the words. Actually, you shuffle kind of n-grams. We tried to use TTS, but then you have the issue that TTS is not like ideal and you have the years of the TTS itself. So maybe it's not ideal experiment. And then we did the human recordings on the shuffled sentences and asked them, to record like many sentences and see how we perform there. So in that sense, every experiment has its own like systematic errors you can think about. But at the same time, if you see the trend everywhere, it's kind of proving that maybe we are like improving either linguistic or acoustic. So if we see improvement on the shuffled sentences, that means that we're learning acoustic also because linguistic kind of like hidden in this test. So what we see is that, yes, we learn better acoustic. So in all three experiments, almost in all the cases, we see that the model where you have additional like unlabeled data, you improving on top of the training of only unlabeled data. And then, of course, if you have the recognition on the like original sentences, you get way better performance, which means that you are measuring in domain performance. But also it means that the model itself is actually learning linguistic, and we're improving linguistic too. So how can we test also that linguistic improve too? So in that sense, we can look just at the beam search decoding and see how the model performs here. Because we use the n-gram decoding for the pseudo labels generation, the question is, did we transfer this model n-gram representation to the acoustic model now? And what we saw then, when you decode the model trained on labeled and unlabeled data, we don't see improvements anymore with n-gram decoding. It doesn't helpful. That means actually we transition the n-gram language model to the acoustic when we learned on pseudo-labeled data.
Can I ask a question?
Yes.
So I missed, you're scrambling the training data as well?
No.
So just the evaluation?
Just evaluation, yes.
So I must be missing something, but so you wouldn't expect the n-gram language model to help them, right?
No. For this one, we do, it's original data, no scrambling.
Okay.
Only for that thing, we do scrambling. There is no language model involved.
Okay, so the scrambled ones are the two to the right.
Okay, so 3 experiments. Left is the segmented data, scrambled. The middle is TTS generated for scrambled sentences, and the last one is human recordings. And then here you could see that LibreSpeech shuffled, which is the light orange, let's say. This one is on just the model trained on labeled data only, evaluated on the shuffled sentences. Okay. And then the gray one is when you have the model trained on labeled and unlabeled data, evaluated on the shuffled sentences. And then the two, the blue one and red one, the same models, but when you do this on original data order.
Okay, so one more clarification question.
Yeah.
So when you scramble the audio, you're actually just taking the audio file, segmenting it, and
Yes. Yes.
Play these. What I mean, I imagine they sound.
It's fine.
Okay, but doesn't it totally kill the prosody basically? Because the human reading, I mean, I could put a reasonable prosody even into that scrambled sentence, right? Even though it's syntactic garbage. But I would imagine that the audio segmentation scrambling would be just. It's pretty strange.
It's you have the border effect of the segmentation, but the problem with segmentation, we did this keeping you segment when you have the duration, like the silence duration more than 1 second, for example. So in that sense, you don't have really one word shuffling. That's the problem with this experiment, because you're still keeping kind of n-gram statistics in the audio, and that's why shuffling segments is kind of okay for the prosody, because you have most likely you have 3-4 grams in the data.
Okay. Okay, and then so this is. I'm sorry, just having trouble.
No, it's okay.
Swallowing all this at once. Is there what's the takeaway from this?
The takeaway is that if you have the model which is additionally trained on a huge amount of unlabeled data, we improving acoustic. Okay. So you can see that the dark gray is lower in most all experiment, like in almost all bars here than the light orange. That means that you are learning. So on the scrambled sentences, your model, which is trained on unlabeled data in addition, it's better, which means that you kind of not having the dependence on the language, so that I can reconstruct some word because I know the language, like prefix. I'm reconstructing because I just have better acoustic representation.
Okay, thanks.
Any other questions? You good? Okay. Okay, so now the question, I showed you that we can do multiple rounds of pseudo labels, right? And the question is, do we improve here or not? So we did 3 settings where you can consider like a bit lower source setting where you have 100 hours of labeled data. And then you have like additional unlabeled data, either like low scale or high scale. And here we repeat the pseudo label process again and again, getting better model. And then you reuse this model to relabel your data. And what we see that multiple rounds helps as expected. In some cases a lot, in some cases not a lot. But the question is how we can do this in more simple and like efficient way. Because here you can see that we retrain every time model from scratch, and we repeat this process many times, and we even don't know how many times we need to repeat. Google reported that they repeated 5 times and they saturated. We also saw 5 times is enough and use saturates, but this is on LibreSpeech. We're not sure about the real data. So at that time, we decided, okay, how we could make this efficient and avoid a lot of stuff. So we moved to continuous pseudo labeling. So I would say at the beginning, we called it iterative pseudo-labeling, but then over the time, I would say we come up with the name of continuous because it's like better reflects what is actually happening. Okay, so what we decided to do is in this scheme, you're training from scratch. So how about we continue training the same model and we just over the time iteratively regenerate pseudo labels. The problem that if you train till the full convergence with your pseudo labels and now you regenerate, you probably not get much gain because you just already saturated. So now the question is how we can train continuously one model and allowing the like constantly regenerating the pseudo labels. So we come up with the first version of the algorithm, which like we call iterative in this manner. So you have labeled data, you train your acoustic model. So now you have your like unlabeled data, which is a huge pool, and it's very expensive actually to label the huge pool. So what we decided to do, okay, let's just subsample. We found that 20-40% with some synthetic experiment is enough. Let's subsample this amount of data. We label them. And interesting question here, do we need to use beam search with the language model? Because beam search is also expensive. So with synthetic experiments, again, we saw that, yes, you need beam search and language model like creates additional like kind of shift in your labels. And if you don't use this, you get way worse performance. Okay, we generate our pseudo labels with beam search. And now we're just adding this to the back to the training, and we continue the same model training now on the mixture of labeled and newly generated pseudo labeled data. Yes.
Beam search. I mean, what's the size of your beam? Is this like traditional? You could be up to 1,000, but most of the time we're talking about like 5 or 12. Or
no. Okay. So at the time we experimented more with CTC models because beam search is faster there and you highly parallelizable. We use beam search of 1,000.
Okay. Yeah.
Yes, 5 and 10 doesn't work for CTC. No. Yeah. For the sig-to-sig models, if you look at the Google paper where they did a lot of experiments, and I later also did with sig-to-sig, small beam is okay, right? It's enough, but then you have autoregressive generation, so it's slow. So you have kind of okay. If you wanted to measure which one is better to use, you need to like account all these things. Okay, we will go to the beam search in next part. Okay, so now the question also how the augmentation influence. So we decided, okay, do we need to actually augment the data or not? Because pseudo labels are generated on the clean data. You don't augment them. So we measured the thing that if you skip augmentation in your training, and yes, you have like degradation in performance, so you need to have augmentation. So this is the second key component in overall pseudo label process. Okay, and then you train on this like augmented now data with pseudo labels and labeled data for the same model for some time, several iterations, and then you like repeat this process again. So effectively, you can compute how many iterations now we can do, and effectively we were doing more than 25 pseudo label regenerations every 10-20 epochs, and this way we get actually better results. Okay, so now in terms of efficiency, so this is the graph showing you what the word year rate you can reach for the same amount of training time. So you can think that you fix compute budget and now what the word year rate you can reach. So with our like new version of the pseudo labeling, we can get better word year rate. But also if you look at the like what word year rate, okay, if you wanted to achieve the same word year rate, how many days you wanted to train, for example, for the state of the art result, you can see now comparison in terms of like efficiency for the GPU hours you need to spend here. Okay, and at the time we got the state-of-the-art result almost in all the settings, or we got the same like similar kind of performance. But in that sense, we were more efficient in terms of like GPU hours you need to spend for training these models. At that time, Wave2Back 2.0 is not appeared yet. Just a disclaimer. Okay. So now you could ask the question, is it enough for our training? Maybe now I have a best model and I can do better pseudo label generation. So now you can just use this final model to regenerate pseudo labels, and now retraining the model from scratch entirely, forget all the stuff which you know, kind of forgetting maybe is a good way in our case, and retrain the model. So we did this experiment and we got the same result. So we kind of saturated, at least with our process, whatever we could get out of that with a like scheme of the training. Okay, so now going back to the beam search. what is the problems with this training? I gave you the nice picture that it's so good, it's so efficient, but there are problems. So first of all, we found that you overfit to language model, which you use during generation. So here we try to regularize this by restricting language model weight, of course, but it's a bit of tricky if you want to really like use this in practice. The second one is beam search is still expensive. You still run it a lot of time and it's still a lot of overhead, especially you run this on CPU, which means that your GPU is wasting, but also you can think, okay, maybe we can do nowadays beam search on the GPU, still maybe not so efficient. Okay, now the question, can we remove the language model from the process? The answer is yes, and I will show how we do that. And moreover, we had a problems of extending this process to low resource setting. It was not working really well, and at the time, wave-to-back 2.0 appeared, so we could not beat with 10 hours labeled data setting. Okay, so how can we solve this problem? So before we used hard labels, it's just transcriptions, and we use the beam search, where you see here the red component, which adding the language model with the beam size of k, which is 1000 in our case. So now we want to just to remove the beam search and language model and just approximate with just hard labels as argmax of the probability. So for CTC, it's just argmax of like per every frame to get the transcription. So now how we can make it work? So you need to make some modification. And the main issue is stability of the training. So what we propose to do is we propose to add the cache, so-called, which means that you have your labeled data, you train a little bit your acoustic model, and then you start to generate pseudo labels on the like unlabeled data, and you put them to the cache, and you train for some time, and you have some probability of removing from the cache. So now going to a bit to detail. So what's happening is here. So you take the batch of the unlabeled data, you take current model state, you predict pseudo labels just as argmax of the probability of acoustic model, and you place this sample into the cache. Okay, so now how you like remove from the cache? At next future iteration, you take the sample, you take its pseudo label, which was generated by the model state at the previous step, you train on this sample, and then with some probability, you return back to the cache. So why this probability is important? Because this creates efficiency so that you don't need to, regenerate pseudo labels. So you don't need to run additional forward pass. And the probability often is very high to return back to the cache. And at the same time, reusing the previous states of the model, it's helping to avoid collapse because of absence of beam search, because of absence of language model, which gives you stabilization of the overall training. Okay, so one of the prior works did similar thing in terms of just regenerating pseudo labels after each iteration, and that was work from Amazon without beam search and without language model. The main thing for them was training entirely till full convergence and then doing pseudo label process. And this may be not efficient because you kind of overfit to your labeled data, and now you start to use some unlabeled data, so you have huge bias over that, and this is not good for performance in the end. The second thing, if you try to do this now a bit early in the training, not waiting till full convergence, which we want to do, you will observe instability. And here I show you example of instability, and it's very fine instability. Sometimes you diverge and nothing else, but sometimes you kind of diverge, you see what your rate is 100%, but then you start to converge again back, and this is super weird optimization. And what is interesting, in the end, you can come up with the same model performance, even if you kind of having these peaks over the training. So it's really non-smooth optimization in some sense. So that's why we did kind of cache mechanism which stabilizes the training, and you don't have any issues with divergence, and you don't need to rerun your training again and again. Okay, so how you do this in practice? So you just train your supervised model, whatever is it, on your labeled data, and then you start to do pseudo label process with this semi-PL algorithm, just decreasing the dropout of the model. So you wanted to increase the model capacity because now you have a lot of unlabeled data on which you wanted to train more. So in the end, we got the best pseudo label technique, and we almost closed the gap with wave-to-back 2.0. Before it was super big gap, now it's a little bit gap. And in terms of not low resource setting, we got state of the art without any additional language model decoding. And we got on par results if you use language model decoding with wave2vec 2.0. So at that time, it was the main baseline to beat, kind of. So we achieved that and showed that, yeah, okay, pseudo labeling is kind of good strategy, and it's a bit simpler to train compared to SSL. So SSL is really heavy, and I know that hyperparameters, if you switch to another data set, is really hard to do. For pseudo labeling, you can read in my papers, you can just use the same parameters for other data set, and it's going to work for sure. So how about efficiency now? Because we have this probability going to the cache, you removed also the beam search. So here is comparison of GPU TPU days to get this like state-of-the-art result, comparison to wave2vec, and also compared to previous algorithms. So it's way more efficient. So now, yeah, as I said, CMIPL is very robust. So if you have kind of a little bit enough labeled data, so then it's very robust to hyperparameters. You can change whatever, and it's kind of stable, giving you very close results. And if you have limited data, you need to be careful a little bit about the proportion and the cache, but that's kind of simple to tune. Okay, so at the same time, like several works come up, and in my paper, I did this as ablation. How about doing continuous pseudo labeling with exponential moving average? So you can think that what we were doing, having this previous state model reusable for the pseudo labels, you kind of doing model averaging, and the cache kind of stabilizing the training and computationally efficient. But we can go for other strategy for averaging of the models, and this is exponential moving averaging, which you probably found this nowadays in many papers and in many like solutions. So in that sense, you can just keep track of the current model as exponential moving average, and you just use this model to generate pseudo labels. And I did this as ablation, and this works very well. And nowadays, like a bunch of people, I see that they're using actually EMA for pseudo label training. And myself, I use it when I need to, very fast implementation, because it's way simpler to implement. And when you do this ablation, we see that dynamic cache and EMA kind of does not perform better if you combine them together, because you can combine them together. At the same time, they perform kind of similar. But the main issue with EMA is that you need to have more memory, because you keep the second model on your device. So this is maybe not the practical case. And the second thing is you regenerate pseudo labels every training step, which is also expensive because you call the for pass again and again. So in that sense, kind of, way more simpler algorithm. So you can use EMA just to run and, check if it's working and what the performance you can expect. But then maybe if you wanted to do some additional optimization on the efficiency side, you can go with a cache solution, for example. Okay. Now, because we're competing with SSL a lot and trying to sell that pseudo labeling is a bit more simpler in practice, you could ask the question, how about combining them together? And we had the same question, and we did collaboration with the wave2vec team. And we found that, yeah, okay, they're kind of complementary in the sense that if you combine them together, you can improve performance. But the question is why this happens, or what makes them different, so that the combination of them helping you to improve the performance. And kind of by accident, we did analysis with my summer intern. Then what are the differences between pseudo label process and SSL? And one discrepancy which we found is dependence on the speakers and dependence on the number of hours. So now let's assume that I wanted to have control experiments, what I need in my data, more speakers or more hours. So let's assume that I have now control experiments where I have the same amount of hours, which is fixed, but then I vary the number of speakers, which means that every speaker will speak less, but I have more speakers. Or vice versa, you fix the number of speakers and now you increase the number of hours. So you're saying the same speaker will record more audio. So we did this experiment with LibreSpeech. It's limited. So this is for sure should be checked on the large scale, like more diverse data. So we just restricted to the LibreSpeech in terms of even combinations, which you can try in this case. But what we saw is the following. So here you see dependence across all the settings. We average now the performance, and we show the 2D graph instead of 4D graph because you have four variables actually here. We show the average performance. So here you see dependence between unlabeled speakers and labeled speakers. And you can see that in pseudo-labeling, we depend on both of them, and having the proper number of speakers and labeled set is super important. Even for supervised training, if you look at this, you need to have enough speakers. While in self-supervised training, you actually see that you're more dependent on the unlabeled speakers rather than in labeled speakers. Maybe because you train first on unlabeled data and then you transfer to the labeled data with fine tuning. And here, it doesn't matter what you see in labeled data anymore because you saw enough speakers during the pre-training phase. The second thing is how we depend on number of hours. So in pseudo-labeling, we see that you depend on both of them. So you need to have enough labeled hours. And that's why it's hard to beat the SSL methods with pseudo-labeling in low resource settings. While in SSL, you can see that you highly depend on unlabeled number of hours. So if you don't have enough pre-training data, you don't get very good results, actually. So the dependence here is very different. And this is aligned with other work also, which try to dissect a bit how SSL depends on different factors. So it's really different dynamics of the training during initial phases, which are super important for pseudo-labeling and then for SSL too. Okay, so why we stop at the hard labels? How about going to soft labels? So we kind of asked the same question, and we thought, okay, actually, if you specify the whole distribution, I know more about the data. I even know about all the sequences and what the possible transcriptions could be. Why not using that? And we thought, okay, let's try that. And this is an example of the work which didn't work. And this is negative result, but still you can publish sometimes this kind of work. So we tried to apply like soft labeling, and what we saw is that it's always collapsing to degenerate solution. We most of the time see that it's starting to produce purely blanks because it's CTC model, or it start to produce somewhat just letter which is repeated. And we tried many different regularization, including many variants of the entropy regularization, but nothing worked. And we thought, okay, let's go back to transcription instead of like probability, how we can get kind of distribution, like rigid distribution, staying in the transcription level. So you can think about, again, let's do beam search and then use all transcriptions which you have in the beam search. And then we saw, okay, that's actually helping, especially in low resource setting. This really like matters. Then you can think, okay, how about sampling from the distribution? It's also will be covering kind of distribution. And we see that, yes, okay, it's stable, it's working, and sometimes it's improving a little bit performance. So now the question, why it's not working for the like full soft labeling, which is claimed in other papers in Vision, especially that soft labeling is way better than the hard labels and it's better to do. So the issue which we like came up after investigating what's happening with the training is that you have two kind of notions here for speech. And I want to highlight here, this is the main difference between the speech and vision. And this is the reason why you should study also sequences and not just images. It's because you have frame level consistency and sequence level consistency. So soft labeling and the losses on soft labeling imposes the frame level consistency. And you see here that the green one on the right plot is, it's right to you or left to you. Okay, on the left plot is lower than the other thing. So that means that the distances between the frames is more closer. So it's more smoother. But then if you look at the sequence level consistency, that transcription, which actually you produce, because you don't care about the probabilities of every like frame, you're interested how the letters or the frames put together into the sequence. That's actually like worse, and it's broken after some time of the training. So the issue which we found is that the loss on soft labels, which is classic in computer vision, does not impose sequence consistency for the speech data. So in that sense, we unexpectedly found that soft labels lead to divergence. You need to have like sequence level additional loss function. And one of the things we tried to impose, you kind of just filter out the things which breaks the consistency of the sequence, and this kind of working. I didn't finish this like fully work, but that was the main kind of preliminary finding here. Okay, so another aspect you could ask how long we should train the model on the labeled data before we go to the like pseudo label process, and we tried to understand this like with my intern. And here the main thing is you wanted to skip maybe a phase of this like pre-training on the labeled data only and go directly to pseudo labels. So here what we did is we analyzed a bit how you depend on the starting point. So we see that actually if you train longer, you kind of performs worse actually. But if you train very short or no training at all, this could lead to instability and divergence of the training. So we try to analyze and see, can we remove actually the acoustic model at all for the pre-training on the labeled data? And the answer is actually yes, but we need to understand a bit better evolution, how the pseudo labels actually changing. So first thing is we try to see what happens if it like play a bit with the cache probability, and we see that at the beginning of the training, it's better to keep the to keep the samples in the cache, so you don't try to remove them. So that means that kind of you're trying to just learn on this and overfit on these samples. While later in the training, it's better actually to see diverse data and just update your cache more frequently and see more examples. And having this, we come up with like solution in the sense that let's just compute how the pseudo labels actually change over the time. And if they change too much, then we keep maybe, or if it don't change much, we remove it. And this depends actually on the time of the training. So at the beginning, we wanted to keep the samples if it changed a lot, but then later in the training, we wanted to remove the samples otherwise. And with this technique, we got that now training is mostly stable and we can get even a bit better performance. This is what was our target was, not overfit to label the data, especially in the low regime setting. So still, you can sometimes observe instability, and to fix this, we said, okay, let's just sample sometimes the transcriptions as we did in soft labeling, and like we actually find that yes, you can do that, and this will be stable, but then you have a degradation in performance, and that's why you need to have kind of temperature linear rule overall to stabilize the training. So in that sense, we did experiments on Libre speech and also like common voice, like other language, like French. And we see that, yes, you can train without any pre-training on the labeled data. You can get similar or a little bit better performance actually in low resource setting where you have 10 hours of labeled data. But overall, let's say, I would say this is more for understanding and learning something about pseudo labels rather than using this in practice. This is really hard to make it stable, and a little bit tweaks are needed. So it's not really practical if you want to just, go and apply it to low resource. But I would say if you want to apply it to low resource, everything will be complicated because of high overfitting on the like 10 hours or 1 hour of the labeled data. Okay, the final thing on pseudo labeling, which I wanted to cover is maybe more interesting thing, the recent work. Can you apply this to multilingual setting? So we actually we did the first work on pseudo labeling for multilingual and showed how you can do that. It's also non-trivial because you have many languages and they compete with each other, and you need to stabilize now. Now you understand better that there is issue with stabilization, especially with low resource, and you have this additional competition between the languages, which is non-trivial. But now I wanted to show you other actually maybe more interesting work in the sense that can we do cross-lingual transfer? So assume that, okay, so prior works show that if you have some labeled data for the target language, we can do the training. So you do fine tuning on the target data. Now assume that you don't have any like labeled data for the target language, you have just unlabeled data. So what you can do, what you can do here. So we wanted to transfer actually the model from one language to another language. So now assume that I have a Swahili language, and here is the ground truth for the audio. And if I apply English language model, and you often use language model, of course, English acoustic model on top of that, and you often use a language model, so you can see the transcription here, which is out of entirely from the ground truth. So now, how about if I'm just applying the English acoustic model? In this case, you can see that it's doing way better in terms of capturing pronunciation parts, right? So now what's happened if now I use target Swahili language model on top of that? You can actually fix a bunch of things. So that was the idea which we decided to, to tackle and understand a bit better how the languages actually transfer between each other, and can you apply one language to another language? And we found interesting dependency here. So first thing is, so how are we going to do this process? So you have your often labeled data, you have acoustic model, language model, and then you do pseudo-label generation. But now we're going to have a target language where we have only like unlabeled data. So what we do, we apply English as a source acoustic model. We use target language model, and then we generate first seed of the pseudo-labels, and then we just reiterate from the pseudo-labels itself. You don't have any labeled data, just from itself. So first of all, it's maybe a hard problem to reiterate from its own, but here you have the grounding source of the target language model, which can help you. So we did a bunch of source target transitions. So here you can see many different languages. And here is the result. So this is if you apply, okay, so you have language and then the arrow. So that means this is target language. And then at the bottom, you have the languages to which we transfer. So main thing is seeing here the trend. So this is your source acoustic model, which you apply from, for example, the most left plot from English to like Spanish, German, French, Swahili, and Hausa. So it's all awful word year rate as expected. So then you're adding the target language, and you can see that a bunch of languages actually decrease significantly. Now the question, is it enough performance of word year rate from which you can bootstrap? And eventually we see that, yes, for some languages, for some pairs of the languages, you can transfer very well. And even kind of sometimes you can reach a little bit close to the supervised, fully supervised training. So here, interesting thing is you can transfer everything to Spanish. So Spanish is simple language in terms of pronunciation. And you cannot transfer anything to French. So French eventually in this set of languages was the most complicated because it has a very diverse prosody and omitting a lot of, like for the letters, you are omitting a lot of, for sounds, you are omitting a lot of letters in the pronunciation. So it's super hard to transfer from other languages to French. If you look at the like pseudo labels, how they're progressing, so this is the example, what's happening. So you can see that over the time, it's actually fixing some errors in the transcription. And we see that source language matters. So you really need to have some correlation between the source and target language. If they are not related at all, it's kind of hard to do the transition. And moreover, you depend, of course, on the source and target audio size. So if you have more source labeled data, better model you get, better transfer you can have for the target language. And the same in target language. If you have more hours of the data, you can get better model. Interesting thing, you could ask, what happens if you have different like alphabet? And we try this too, and yes, it's possible. It's super hard, but it's possible. So you need to have kind of correspondence between the sounds or characters, and then you kind of can do this transfer. Yes, the word error is still high, but if you look at all the works where you have pure unlabeled data for the language, it's actually not so bad. Okay. So, I hope I pursue that pseudo-labeling overall is a powerful practical tool. Yes, SSL is still dominating. Yes, still people don't like pseudo-labeling papers and they write like reviews, oh, did you compare with SSL, etc. But in practice, it's really way simpler to train. And this is like gives you out of the box right away improvements on top of the supervised model. Okay, so now let's go to efficient speech generation. So right now, if you look at the TTS systems, they are heavy. They're trying to model at the same time content and acoustic features. That's why you have two set of the features. And right now, at least now, finally, we have receipts for autoregressive generative models, and we can try to use them. And people trying to use like back to autoregressive TTS systems. The training also in multimodality works is that we're trying to embed every modality together into the general space of the tokens and then use autoregressive models, and all this works around like LLM findings, right? So now for us, the question was, can we do efficient joint training for ISR and TTS? And can we simplify actually the tokenization from the current like TTS well-used tokens? So in general, from our research and kind of what people are talking right now is that we really need to have very careful tokenization strategy for a lot of generative models. And the same like calls for like TTS and ISR. So the thing is, if you look at the current like TTS, there is tokenizer aiming for semantic content, which is like Hubert k-means or wave-to-vec features. And there is other which trying to have the audio content itself, right? So encoding and speech tokenizer. Now the question is, if you wanted to do joint modeling for ISR and for TTS, we need to have both of them at the same time. So how we could achieve this with one tokenization without using two of them? So in that sense, we know that vocoders work very well for MEL filter banks, and we know that MEL filter banks actually have very good features. So now the question, can we just use the simple MEL filter banks itself for the tokenization? And that's exactly what we did. We call this DMEL. So you have your filter banks, and now you just tokenize it. So it means that you just discretize the every bin of your like frequency for a particular time frame into specific bin index. So the tokenization process is also simple. You just have inverted function. So you don't need to have a heavy encoder like in other tokenization. And then you get your like tokenized like features here. You can see that, yes, we have the loss of information, but now the question, how much loss we have? Okay, so in general, why we decided to do something so trivial, mainly because MEL spectral grounded in the human perceptual bias. So we don't need to have like encoder. In that sense, we can use just off-the-shelf vocoders for the raw wave reconstruction. And if you look at the quantization itself, how well like it's working or how much information we lose, we look first on the content base, measuring the word hear rate by some ISR system. And you see here the last row, that the last two rows, that from the discretization itself, you don't lose much information. So it's the same. And then in terms of perceptual thing, a little bit loss, but overall it's still on par and kind of trade-off between the content-based and acoustic-based tokenization, which exists. Now the question is how we use this discretization to kind of embed this into the model training. So we take the time frame T, we have the filter banks, like 80 filter banks here. So we discretize every filter bank here into the bin. So here you got the, for example, 2, 8, 10 bins for the last three frequencies. Now what we do is we take every bin, we map every like bin token into the embedding. We repeat this for another one, and then we stack them together. And this will be our representation for the time T. Yes.
Usually, people use like oral to set that code.
You mean for the binarization itself?
I mean, but in the last slide, there are 8
Oh, okay. So, no, okay. It's actually 2 in power, but we need 2 bins for the end of sentence and begin of sentence. So, yeah, that's why. So yeah, we use this power of n. So if you go to the paper, it's exactly that. But then you have additional special tokens which you need to cover. Okay, so you stack for every bin frequency. You map this to the embedding. You stack all embeddings, and this is your representation for the time T. So now we have the unified speech text decoder, which means that you have your kind of, okay. I don't know why everyone calling now decoder architecture as LLM. This is for me kind of strange thing. So this is really decoder architecture. So now you have you prefixing begin of sentence for the modality, then you have your first modality, then you have end of sentence, and then you're prefixing the second modality. And now you wanted to produce the second modality. So here you have only causal self-attention, without any cross-attention mechanism. So purely decoder architecture. So now if we wanted to solve the TTS task, which is text to speech, so in this case, you prefix the tokens in the text domain, then you prefix your mapping of these bins to the representation, right, in your speech domain. And what is interesting here, we model all the frequencies in parallel. So we're predicting all the tokens for the time T in parallel, so 80 of them. In case of ISR, we take speech as an input, as a first modality, and text as an output. So in this case, you have your, again, speech part, which is with this DML tokenization, and then text tokens, and then you predict one token. Okay, my screen disappeared here. Is it fine? Okay. Yes.
Tokens, Have you considered the relationship or dependency between different tokens? Like for each frame, maybe the first token is related to the second token, so like the first token.
Yeah, okay. So you're asking why we do in parallel prediction instead of kind of, okay, the parallel prediction was designed because of the efficiency. We wanted to do this faster and not doing RVQ tokens like in speech tokenizer, where you have this hierarchical generation and even autoregressive stuff. It's a good question, research question in terms of, do we need to model something else or not? I agree with you. Main thing is efficiency. We want it to be efficient. It's kind of CTC, right? But we know that for CTC at scale now, if you train on a lot of data, it's okay. It's learning language model too. Even though you're saying it's independent, but we're learning because of the transformer and because of the previous layers.
Yeah, the dependency is already shown in the last hidden layer of the transformer.
You can't do that, right? Because you have all of them and then you have a transformer and you have a mixing of the tokens. So that's all happening inside the model. And maybe you don't need to have at the last step. Yes, I agree. Okay, so one important thing here compared to other works is that here the issue that the frames are highly correlated. So to overcome this issue compared to other tokenization, we need to mutate the inputs and doing like additional like heavy masking to overcome this correlation. And of course, if you have too big, like if you like change the temporal resolution and using bigger strides, so of course this like hurting the overall content and overall reconstruction, and you hurt the audio generation performance. But overall, it's still working in the sense of content preservation. Okay, so in the end, we did experiments on the Libre speech, which is noisy, and compared to different tokenization, which we implemented ourselves in our like code base of the model. So we see that discretized filter banks working better for the TTS. They working better for the ISR task. But now the question you can see here, the ISR itself on Libre speech is 10%, where I showed you before on pseudo labeling, for example, I don't know, 5, 4, 3, something like that. Why is this gap exists? So we try to understand why this gap exists, and like main outcome is that it's overfits probably heavily because it's a decoder architecture. And we did experiments with the MEL and DMEL like representation for the standard CTC model or encoder decoder model, and you can see here that they are kind of on par. So discretization itself do not affect the decoder performance. It's really decoder architecture issue rather than encoder or encoder decoder. And you can see these issues right now in machine translation. People reported similar thing and other domains, so that decoder architecture can be behind the architectures where you have cross attention, for example. Okay, and then finally we modeled it jointly like ISR and TTS because now we have the joint tokenization. So we were able to keep the same performance for the TTS for the joint model training, but then ISR is a bit behind and seems to be undertrained. So we see the issue of joint model training, which also other people reported in the papers recently, that it's hard to train jointly these two tasks. And you have the issue like synchronization, the two kind of like tasks and the pace of the training of the tasks. Okay, so in the end, deeper research on unified tokenization is needed here. So how we could unify recognition and generation in general. So here we thought, okay, so how about thinking about denoising speech recognition. So the years which we are doing, actually, they are related to ISR, and they are not related to the language modeling. And language models fixing us something different than what we have in speech recognition. So in that sense, what we thought, okay, let's just predict transcription from the ISR, and then just use TTS generated data and saying that now we have the pairs of the true transcription and the transcription which we obtained from the ISR, and just try to learn language model which will be doing denoising and not learning all the structure of the language. So this is not the new idea. I'm not selling this. So this is error correction models, very well studied. People use this for a long time and try this stuff. And even people tried the TTS to generate this stuff. But the main issue is that they didn't show in the past that if you use TTS system, it can outperform the conventional language model in the beam search or like fusion like methods. And here we show that actually it's possible. And if you have large scale and proper TTS data, you can actually overcome that and outperform the conventional language models. So the main like details for the thing is you need to have like proper like augmentation, otherwise you overfit. So you need to have random substitution of input text. We also masking the spectrogram, so you have standard like spec augment part of the frequency. We use multiple TTS system. An important thing here is multi-speaker. So if you have just one speaker, it's not going to work. And we trying to combine also real data and synthetic. Even if real data is small, it's okay. It's helping overall training. So in the end, we were able to get the state-of-the-art result for on the Libre speech with denoising language model on top, and even close like performance with SSL methods here. And in terms of like conventional language model, we were able to outperform them and showing finally that error correction model can be better actually than the standard language model. We tested overall how we can perform in terms of like different architectures, and it's applicable. We check the scaling, so the model size, if you increase the model size or data size, it actually becomes better. It's kind of practical because you can do ISR on device and then just send all transcriptions to the server, and then it will be doing denoising of these transcriptions. And finally, you can ask how synthetic data important, or maybe they are introducing some errors and we underperform us actually. So thanks to Libre heavy dataset, which created the LibreVox labeled data. So we use this data to test this hypothesis. So we actually see that in terms of performance, real data and synthetic data performs kind of on par, and they're close. So you don't really lose a lot with synthetic generation here. Okay, so in the end, the error correction models work at scale. Okay, and finally, privacy. I know I'm a bit out of the time, but a little bit. Let me try to finish. In the time which I have for the presentation, and then if you have any other questions, I am happy to stay and answer any questions, whatever you have. Okay, so privacy. I started to work 2 years ago about on privacy, and mainly I see the gap that privacy is studied for language models now a bit, and in general for computer vision, but nothing or not many works in speech, let's say. So there is federated learning, but not many privacy. But people claimed already about privacy. There are issues of like learning in terms of on-speech data. So why we in general wanted to have kind of privacy and federated learning? Because your training depends on the data and like storage of all this data, and we can really distribute this over our, for example, phones, and just do it more efficient way. The same thing is we keep actually private our data, so no one knows what you have, and in that sense, maybe you will be more willing to share your data for the training and improving the models for yourself if you know that your data are private. The problem in speech right now, it's really like standalone domain, so people trying something, but main community of federated learning and privacy, they do not work with speech at all, and they don't know the speech at all. That's what I see right now. There are started a bit of works in the past years, which is good, and this is what we're going to discuss today. So if you're not familiar with federated learning, I will give a quick intro. So what's happening is you have a server model, you initialize it, then you send this model to the devices. You train locally on these devices for some kind of steps. If you train only one step and send back to the server, this means your central training, it's equivalent. But if you do several steps, it means that you do a bit different optimization process. After training, you send back the updates, so your gradients actually from the model to the server, and then server aggregates these updates and update the model. And then you repeat this process again and again. You can do multiple epochs instead of like steps, and then the issue of kind of proper synchronizing these things, because the amount of data on every client can be different. Okay, so why this problem is different? Like it's different, but also it's harder, because in RGD you just do this step. In federated learning, you do like the step on the right. So you can see that your optimization is entirely different, and you need to have kind of aligning all the devices to be in the same direction, so that your optimization is actually moving and not just stalling. If you add differential privacy shortly without going to the math, what it means that you adding the noise to the gradients before you averaging them, and this noise actually guarantees that with the high probability which connects to this noise. So you need to add a lot of noise. Then with high probability, you cannot say if you trained on your data or not for the model. So if you train the model on your data or you exclude your data from the whole batch of the data, then you cannot distinguish these two models. That's what eventually differential privacy tells you. So you have a lot of different issues like data heterogeneity, training from scratch, like training from seed model, which is out of domain, also communication, and of course, these like noisy gradients for the privacy. So in that sense, it's all very hard. And moreover, the question how it's working for ISR and moreover, how it's working for ISR of the models which we're using right now, which is, okay, less than 1 billion, but it's already like million parameters and it's not clear. So first of all, we claim that ISR is a suitable benchmark. So we looked in the common voice data set, and you can see that the distribution there is kind of heterogeneous. So you have very different variations between the different speakers, and also you have multilingual availability here. But the common voice is not ideal data set. So it's good data set to start research, but we need more data sets here. So speech also is good because you have classification and segmentation. So it's more harder than what people doing in vision. And of course, you have this like acoustic and linguistic variation. So you actually can create many different variations in terms of how the data distributed in your federated setup. Okay, so first question is what's happening with the models themselves? So right now, most of the papers reported results on the small models, and of course it's clear because it's simpler to train, less communication cost, but we don't know really how the large models working for the federated learning. And if the federated learning optimization is hard due to like this federated regime itself, or it's because of model size, because we know that at scale, model size is working very well now, right? So we scale very well our models. We don't know this for federated learning. So we try to set kind of practical setup. We consider bigger models. We consider the training with a restricted number of steps, because this is practical, and often people consider, million iterations, while we set just 2,000 steps of central training. And we focus on transformers. So why transformers? So first is everyone is using them now. That's an important part of our research, right? But one interesting thing is adaptive optimization is super important for transformers. And what is interesting, people show that in federated learning, adaptive optimization is necessary to improve the optimization. So here you kind of have alignment, actually, how you can train transformer more effective in federated regime. The second thing is gradient clipping. We cannot train without gradient clipping, but it's interesting that in differential privacy, you need to have a clipping. It's connected to the noise. Either you do like a lot of noise or you do like a little bit noise, but then you do clipping of the gradient. So you lose information in your gradients. And this is also aligned for the optimization. Okay, so what we mainly did, we tried to build the benchmarks for the speech, and we show what is the difference with the prior works in general federated learning and differential privacy, what people reported. So first thing is adaptive optimizers suppress heterogeneity like in the gradients of the clients. And we see this, for example, here. So Yogi is more adaptive optimizer than Adam. And you can see that the correlation between the neighboring steps of the optimization is actually closer to each other than in Adam, which means that it's kind of more aligned in the optimization. So the next thing is question, can we train without seed model, or how the seed model from out of domain distribution actually influence? And overall, we see that it doesn't matter. We can train with without seed model with a proper configuration of optimization. And the second thing is out of domain seed is fine. It's working, and you just need to have a bigger cohort size in the training. So we see that if you increase just the cohort size, you actually almost closing the gap with the central training, and we almost able actually reproduce the central training for speech recognition, which previously people claimed that you cannot do. You cannot even converge sometimes for some optimization. Now we actually showing that it's possible for the larger models. Okay, so I almost skip. So then data heterogeneity. So we see a bit of discrepancy between transformers and conformers. So for people in speech, it's interesting finding. For some reason, it's really different behavior. We don't understand why right now, but transformers, it's a bit more stable with respect to optimization than conformers. So robustness. So we just built our federated learning like benchmarks. We tested all in English. We optimized everything. Now the question, is it actually working if it just transfers? So we just applied everything the same for German and French data, and it worked. And we see the same trends, the same dependency between the the cohort size, for example, and optimization. So now there was no differential privacy benchmark in speech. So we did the first differential privacy benchmark. So we decided, okay, let's be more realistic. We have a seed model. We start with like seed model, which is trained on OD data. And then we do federated learning with differential privacy. So here, interesting thing that what we found is that you have imbalanced gradients in overall training, which is very different from central training. It doesn't affect anything, but in federated learning regime and differential privacy, it affects a lot. So different layers behaves differently. That means that you need to have different clipping, actually. So in the prior works, people reported it doesn't affect like differential privacy, but here we're showing that yes, it affects, and you need to do the proper clipping between the different layers. So in the end, we're showing that if you do that, that you can improve like either performance, or you can say that now I can increase my level of the noise, which means that you bring more privacy to your models. And it's interesting that it's also model like data dependent. So we see this for English, but we don't see this for French and German. So dependent. Okay, so finally we checked like what the guarantees we could have, and of course you cannot run with millions of users and millions of data. So what we did like extrapolation what people like currently do in practice. So we're trying to extrapolate what the differential guarantee you will have if you increase the population, and we see that at 7 million population you can have differential privacy guarantees with like a little bit loss of the word error rate for that data. So that means that high resource languages can be covered, but low resource at question how we can guarantee the privacy. Okay, so in the end, what I'm trying to tell you, please go ahead and work on the differential privacy federated learning for speech. And moreover, look into the larger models, not larger, larger like LLMs, just even, at the order of millions, how it behaves actually for these kind of tasks. Okay, so in conclusion, we covered 3 topics. I hope you got the efficiency aspect in all of them. And I encourage you to use pseudo labeling if you can in your practice. DML kind of, for now, we found that maybe this is a good alternative, simple alternative to try the modeling tokenization. And finally, I encourage you to work for privacy in speech. So this is our team. So we are searching for interns, of course. So if you're interested to work with us and with the stuff which I told you, we're happy to have you. So please just contact me and ping me if you're interested. And I thank all my collaborators. This could not be done without many people, many co-authors. So it's super hard work from all of them. So I really grateful to work with all of them. And on that, I'm stopping.